I will talk about fair and interpretable decision making in this talk. I know this is a workshop on, deep learning. This is not related to as much related to deep learning, but we are learning things and we're doing classification. So what is fair and interpretable classification? So as we all know, machine learning has made its way into many, many applications, including ones that have societal impacts, such as lending, hiring, college admissions, or parole decisions. Now, in these applications, unlike recommendations or advertising, the result of the ML algorithm affects human beings, and such they are also not totally automated, and there's a human in the loop because these are critical decisions. And once you have a human in the loop, obviously domain experts, these humans, would like to understand, criticize the model, machine learning model, so that they can trust it. And clearly, these decisions need to be controlled, both, moral reasons and legal reasons, because they are affecting human beings. So by that, there's an increasing need for designing algorithms that are interpretable so that they can be understood by humans. Moreover, since the decisions are affecting people at the end, these need to be fair to those who are affected by the decisions. So this is, the general spiel to justify interpretability and also fairness. Now, to be clear, neither interpretability nor fairness come for free, because at the end of the day, we want to design a accurate classifier. And once you start putting more constraints on the decision making, obviously you might lose some accuracy, and you want to control that and measure that as well. With that, let's move on to our context. We will be looking at binaries classification, supervised binary classification, where we have labeled data with a bunch of features, and the goal of the classifier is to decide on the label of unseen data with high accuracy. You want to minimize the probability of making errors on unseen data. So this is the basic supervised binary classification setting. When you move into fair classification, we assume that data has one more feature, one more protected feature, which denotes the subpopulation the data point belongs to. We have the population, the general population of the data, and then we segment it into groups based on things like race or gender or things like that. And now our purpose is to design an accurate classifier, which also is fair to each group. And I'll define what I mean by being fair to each group more precisely later. So this is the general setting. And I should also mention that in the ML pipeline, you can also, and you should also consider fairness in other stages as well. For example, when preparing your data, you may want to filter out certain features or even data points to encourage fairness of your algorithm. Or after you run your algorithm, instead of outputting the result of the classifier directly, you might want to modify it to improve fairness of your algorithm. With that, now let's move on and explain what we mean by fairness. By fairness, I mean group fairness. And quantifying and measuring fairness is not a very straightforward task. But two well-accepted notions or metrics of fairness are equality of opportunity and equalized odds. So these basically control type 2 and type 2 errors in your classifier. Equality of opportunity metric focuses on the type 2 error, that is false negative rates, and looks at the discrepancy between different subgroups and takes the maximum as the measure of unfairness of the algorithm. So we have, a bunch of subgroups in our population. What we do is we look at the type 2 error in one, type 2 error in the other, take the absolute value as a measure of discrepancy, and we do it for every pair of groups, subgroups in our population. So why differentiate between type 2 and type 1 errors? Well, in certain applications, type 2 error has a more significant impact on the individual involved. For example, if you're talking about a loan approval or college application, refusing a qualified student has a bigger impact on the student than other way around. Another application of this is criminal justice system. Denying parole to a qualified person has a significant impact on the person than otherwise. So equality of opportunity focuses on type 2 error rates and balances them among groups, whereas equalized odds basically looks at both of them, type 1 error and type 2 error, and measures two numbers as the discrepancy of the classifier. So this is what I would consider as fairness criteria in this talk. And I should also mention that when you're interested in fairness and you want to incorporate this into your classifier, you can put it in your objective as a regularization term maybe, or as an additional term, together with accuracy as the objective of the classifier. Or you can explicitly try to constrain the classifier using hard constraints. Our approach is the second one. So we will actually put in hard constraints on the fairness of the classifier, and the objective will be to maximize the accuracy of the classifier. So this is what I mean by fairness. Now let's look at interpretability part of the classifier. Interpretability is not a very well-defined concept. It is basically how well a human being, a user, a domain expert can understand the classifier. In general, simple classifiers are considered, interpretable. And in particular, what we will use in this talk is Boolean rule sets. These are fairly simple classifiers that contain a number of rules in disjunctive normal form. And when you take a data point, you look at these rules. If the data point satisfies at least one of these rules, you classify it as one. It passes the test. And a rule has a number of conditions. Each rule has a number of conditions in it. And a data point satisfies that rule if it meets all of the conditions, hence disjunctive normal form. And here is a simple example. So we have two rules here. The first one has two conditions, and it checks if the third feature of the data point is greater or equal to 3, and seventh feature is blue. If both these things hold for the data point, it is classified as 1, because it satisfies this rule. There are also other rules. The length of the rule set can be variable, and a data point passes the test as long as it satisfies one of the rules. And in general, rule sets are considered, interpretable and explainable because they are fairly simple and people can make sense of the conditions and the rules. And also, if you have, 5,000 rules, each of which with 200 conditions, now you're losing interpretability. So rule sets with fewer rules in them and rules with few conditions in them are preferred. They are considered more interpretable. I should also mention that Boolean rule sets are very similar to decision trees. Decision trees also, make decisions, classify data points by checking a bunch of conditions, and you end up at a decision point in a decision tree if you satisfy all the conditions. Boolean rule sets and decision trees can be translated to each other. So with that, let's move on some assumptions on the data. We will eventually describe an integer programming formulation for choosing best decision rule sets. And for that, we assume that the data has only binary values. That is, instead of real numbers, ordinal features, etc., we only have binary features. And this is not done without loss of generality. because if you have categorical features, for example, this is a fairly standard thing in machine learning, you can binarize it using one-hot coding. So basically, you make a unary encoding of your data point where you start with a feature, say this one, with 5 possible realizations. Then you turn it into a string of 10 binary variables, first 5 of which essentially have the unary encoding of that data. So if your W is V2 here, the second entry would be 1, all these entries would be 0, and then you take the complement of it as well. And for numerical features, you can find a bunch of thresholds, quantiles, deciles, for example, and replace your numerical feature again by a string of zeros and ones, which basically tell you which bucket that real numerical feature belongs to in your thresholding scheme. So what this does is, instead of using more general rules, you can actually turn and find rules that check existence of certain bits in the feature string of your data. Instead of checking a feature is greater than 3 or not blue, etc., you just go check if a certain bit is turned on or not. So your rules simply become a subset of the features. You check their existence. If they are there, you say that the data point has passed the test. To make it a little bit more clear, this is what's happening. If you have a data point with 4 features, let's say, one is a numerical feature, you can pick a bunch of thresholds, and then you can actually turn that feature into a string of zeros and ones by checking where that feature lies in your bucketing scheme or discretization scheme. Same thing with colors. There are 4 colors. So if you have a red being the 4th realization, the binarization of this red, the color feature, would be this string of 8 0 ones. The 4th one here denotes that the color is red, and this one is the complement of it. So existence of these bits are the negation of the existence of the color bits. So there's a 0 here because this data point will fail the test. Is it not red? And similarly, you can translate Boolean features into zeros and ones as well. So you start with a feature space which has cardinal, ordinal values, numeric values, etc., and you turn it into a binary string. So with this setting in mind, one can actually, so one thing to note here is that once you binarize your features, there are only a finite number of realizations of these features. Your feature space is a discrete space now, and it's a finite number of points. And each rule we have checks a subset of these features. And as such, the universe of possible rules becomes finite. Each rule checks a subset of these features. There's a finite number of features. So there is an exponential, but finite number of rules. Now, with this in mind, we can actually formulate a very large integer program which can minimize error on the training set while choosing one of these exponentially many rules. You can write an integer program where variables would say, from among these exponential number of rules, which ones am I picking? It picks rules that have wk equals 1, and these are your variables, binary variables, to choose the rules. And once you choose the rules, you can actually write inequalities that would correctly measure if a data point is classified correctly or not. And you minimize the error terms. So you can write this integer program. Of course, it's not practical to do that. Now, instead of trying to solve or approximately solve this integer program, we actually make as a first step a modification and change the objective function from minimizing error for label 0 data points to minimizing Hamming loss. And in this setting, Hamming loss basically tells you how many rules you need to change in your rule set to classify a data point correctly. A data point that has a label 1, if misclassified, needs at least one more rule that it would classify so that it can be classified correctly. Whereas if you have a 0 label bit, data point, which you misclassified, called it 1, and if it satisfies, say, 3 different rules, then you have to delete all these three rules to classify it correctly. So there is an asymmetry in the classification scheme of the decision rule setting, and we reflect that in the objective function. So in some ways, now we're changing the objective function and trying to formulate the problem with a slightly wrong objective function. But we do this for practical reasons, because as you see, these constraints I deleted, there's an exponential number of them. So the original formulation had exponential number of variables and exponential number of constraints. With this simplification, I get rid of the exponentially many constraints. Now I have a more reasonable size integer program with still an exponential number of variables. And this term simply goes to the objective function because eta is precisely equal to that. So we end up with a, this disappears. We end up with a very clean integer programming formulation. This work I have done with a couple of years ago with my colleagues at IPAM, Sanjeev Dash and Dennis Wei. And computationally, we see that this actually works and it can produce, after doing some engineering, of course, computational engineering, it can produce good decision rules and can have good performance in classification. Now, so far, as you see in this model, I do not have any fairness constraints, right? Fairness considerations. This can be used as an interpretable model, but there is no fairness considerations. Now, moving on, we can now that we have an integer programming model, we can actually add explicit constraints to it. And this is precisely what we do here. For the equality of opportunity metric, these two constraints measure the discrepancy of type 2 error between different subgroups now. Before this accuracy part looks at the whole population. Now in these fairness constraints, we look at subpopulations. And these terms here measure type 2 error for, in this case, we have two different groups, say male, female. They look at the type 2 error on the training data and puts the hard constraint on their difference. Okay, so if you can solve this integer program, it would provide you a decision rule set that makes at most epsilon1 error or discrepancy on type 2 error of the two populations. You can have more populations, of course, with these constraints would increase slightly. But for the purpose of this talk, let's assume that we have only two groups, say male, female, or black, white. And we're interested in balancing the type 2 error made by the classifier on them. So with this, now we have a solid formulation with exponential number of variables, each variable corresponding to a possible rule set. How do we solve this? Now, integer programs are solved by using linear programming, basically enumeration and linear programming. Then the question becomes, how do you solve a exponential size linear program? You do it by column generation. What you do is you take a subset of the variables and then solve the restricted linear program, restricted to those variables only, and then go search from among the missing variables. This would be the whole exponential size LP. You search from among them in a principled way, which is called the pricing problem, to find the most promising missing variable. or in simplex terms, you're looking for the most negative reduced cost column that is not in your formulation yet. So if you can do this, then you can bring that column, in our case, a rule, into your formulation and resolve. And then this loop goes on and on and on until you prove optimality of the LP solution or near optimality. So we know how to solve, not in general, but in many cases, how to solve very large linear programs. So that's what we will do. But then we have to have a way to identify promising rules. We need to solve the pricing problem. Now that has been also nicely formulated in our case, because we know what a rule is. A rule is a collection of features. You check certain bits in your data, and then a rule classifies a data point as 1 or 0 based on the existence of the bits in the data point. I will not get into the details of the formulation here, but basically using the structure of the rule sets and taking the optimal dual solution from your LP formulation, the restricted LP formulation, you can formulate yet another integer program which will find you the best missing rule in your rule set. Okay, so with all of this in mind, let me tell you about our overall computational approach. What we do is, when you get a data set, you divide it into 10 trained test instances. And for each instance, we go through a phase of rule mining, where we try to solve this exponential size linear program with a variety of possible complexity values, allowed complexity of the rule, and fairness levels. So this is a grid. We do the column generation by solving the pricing problem, so that we build the library of good rules. After that, we fix the rule set, and then we go to the rule selection phase, where for different fairness levels that are of interest, we go to tenfold cross-validation to pick the best complexity of the rule, how many rules and how many conditions would there be. And then after this decision, we go run the IP with all the rules that we have generated so far with the chosen complexity, and then we validate the accuracy on the test data. So in all these runs, we have a time limit of 5 minutes. So it is not a super fast approach, but it is not prohibitively expensive either. So with this, let's say a few words about the data sets we're looking at. We look at 3 classical fair machine learning data sets. The first one is adults. Most of you might be familiar with these. It's about income levels based on census data, where the sensitive variable, the groups are genders, male, female in this case. Compass is a more interesting data set, a more important data set in a way, because it's about justice system and making decisions about whether a person should have parole or not. And then the sensitive variable there is race. So our groups are African Americans and Caucasian Americans. And default is about financial application. Here are the basic statistics about the data sets. Compass is the smaller one. The others have 30-some thousand data points in them. So first, I want to say a few words about Hamming loss versus accuracy. Remember, we changed the objective of the classification problem. Instead of solving for accuracy, we're now solving for a wrong objective, Hamming loss. And what this picture tells you is these violent plots have training and testing performance for accuracy and Hamming loss. The story here is that changing the objective from accuracy to Hamming loss does not really make a difference in terms of your final performance on test data, using the right objective. So on the test data, we look at accuracy. So this simplification, as these bars show, reduce the computation time significantly, whereas does not have much of an impact on the performance. So that's a good thing. Now, second thing I want to show you is how well we can control the fairness in our algorithm using the hard constraints. This is the COMPAS data set. Here I have different levels of allowed unfairness. And in this side, we have the true positive rate, this one minus the type 2 error. And here are two groups, group 1 and group 2. And the dotted lines show you what we think we would do in training. And the solid lines are the testing performance. Okay, so this is accuracy, how accuracy for both groups, the error for both groups change as you increase allowed unfairness. And as you can see, what we think the unfairness would be in training really translates to testing. So that way, it is a very robust approach. Moreover, you can really see how the unfairness increases as you increase the threshold. And remember, this was about criminal justice system, and the groups are, based on race. And this group is getting a better deal out of the classification than this one as the error rating or allowable fairness increases. And I don't have to tell you which group this one is. And one other thing, I will show you results later. Around here, you actually get the maximum accuracy, overall accuracy of the algorithm. After that, you may increase accuracy a little bit overall, but not much. But you might be increasing unfairness significantly. So with that, I'm sorry, I'm running out of time. So I will quickly say that we compared our algorithm with 3 other algorithms, state-of-the-art algorithms. 2 of these are logistic regression based, and the third one is a randomized classifier that uses decision trees. And this table has a lot of numbers, but this picture has the same information. What I am showing you here is that this is our algorithm. And we have unfairness on the x-axis and accuracy on the y-axis. As you can see, as we increase allowed unfairness, accuracy increases, right? And these are the other 3 algorithms. So in COMPAS data sets and the default data sets, our approach dominates the other approaches for every fairness level. In adults, however, as you can see, we do well, this is us for a while, after which a logistic regression classifier does better. The reason being, in terms of accuracy, logistic regression performs better in this data set, but in smaller tolerance to, when we have smaller tolerance to unfairness, still our algorithm is better. Okay, so with that, I have one more quick slide. So there are other classifiers, tree-based classifiers, which essentially can generate rules like we do using column generation. So we did one more experiment, and we ran CART, random forest, and fairlearn for a variety of hyperparameters. And once you run them, they produce these trees, which can be translated into rules. And then we went ahead and collected all these rules and put them in our IP machinery to pick the best rule sets. This is a similar approach, described in a very recent paper by Birbil, Edele, and Yüceoğlu. And then we compared the performance of these rule sets. So what we see here is that decision trees give you worse objective, fair decision trees a little better, random forests noticeably better. And when you put all of them together, you actually get a fairly good, you have a large enough pool to pick a fairly good rule set. This one is us. The rule sets that we produce are actually better than what all these other methods can collectively produce. And this is Hamming loss objective, training set accuracy. Let's focus on now test set accuracy. What happens is, as you incorporate more rules from these heuristics, you get better results. When you put all of them, you get a reasonably good accuracy. But our approach, the difference here is the difference in the accuracy for a fixed unfairness level is the improvement given by this column generation framework. And if we combine all of them, all the heuristics and our method, there's an epsilon increase here, not very significant. But what you can do with this is you can use this rules that you can mine from other methods as a warm starting rule set for the column generation procedure. And what it saves us is if we do this, instead of running, say, 50 iterations of column generation, we can run only 20, 25 and still get the same accuracy. So this reduces the computation time a little bit more, but there is still benefit in running column generation, this pricing problem, to obtain good accuracy for given fairness levels. With that, I think I should stop. I'm already over time. If there are any questions, I can take them.